Okay, so we are working on carboxylic acids and esters, and these are functional groups, again, sort of similar to an alcohol and ether, aldehydes and ketones. They have similarities in their functional group with small differences. So you might want to have a bunch of different colors with you. If you're not the kind of person who likes color in their note, then you don't need to. You don't have to worry about that. But especially with esters, I'll use color to sort of split apart the molecule. So if you took grade 12 biology, you would have called this functional group carboxyl group, where you have C double bond O and then potentially OH. So you would have looked at this with certain acids. In biology, you might even focus on acetic anhydrides, amino acids. All of these have carboxyl groups. We are going to, again, focus on the structure, naming, drawing, and properties, as well as the reactions, which will be in the organic reactions note. Okay, so here we have, we'll start with carboxylic acids because they are a little bit more straightforward than esters. So when you have a carboxylic acid, the carboxyl group is always at the end of the chain. So your carbon chain could be 1 carbons, 2 carbons, whatever, however long in length. So again, we're using R to represent that the carbon chain, we're going to follow the same rules and count the longest chain. And then the carboxyl group can be at either end of the chain. So if you're a left hand, if you like to put the functional group, like when you start writing on the left hand of the chain, that's fine. Similar to aldehydes. So it doesn't really matter which end, it just has to be on the end. Okay. So when you name a carboxylic acid, all you have to do is count it. So name the parent chain. So 1 carbon's meth, 2 carbons eth, that sort of thing. And then you drop the ending and add the ending oic acid. So here we have propanoic acid, which is 3 carbons, and then add in the carboxyl functional group and make sure the carbons have 4 bonds, and easy peasy, done. Okay, so the carboxyl group has both an OH, so has an OH as well as a C double bond O. So it's kind of a combo. It's got an OH like an alcohol does, and a C double bond O or carbonyl like an aldehyde or ketone. The key is that both of these functional groups are attached to the same carbon. Okay, and again, always at the end of the chain. So methanoic acid, meth is 1 carbon, so that makes your life a little bit easier. You just have to add in a hydrogen to make sure it has 4 bonds. For number 2, you want to start counting, including this carbon. So we have 1 carbon, 2 carbons, 3 carbons, 4 carbons. So 4 is bute. And then we just write butanoic acid. Sometimes people forget the AN part, so they would write like butoic acid. That's just, bad chemistry grammar. If you wrote butoic acid, even in a normal semester or whatever, I would not take marks off. Okay, the important part is the oic acid part, showing that it's a carboxylic acid and that there are 4 carbons. And how do we know there's 4? Because you've used the prefix or the root bute. Okay, so octanoic acid, you can even use the trick to write out the chain first. 1, 2, 3, 4, 5, 6, 7. And then decide, am I a lefty or a righty? Doesn't really matter. This time I'll put the OH on this side, and then you just have to go back in and make sure your carbons have 4 bonds. If you're a stick person, Each point's a carbon. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then you need an extra line for the OH, and this double bond O comes off the carbon attached to the OH. If you're not a stick person, you can draw condensed like number 2 shown. You can draw it with ticks like I've done the propanoic acid and octanoic acid. It doesn't really matter. Okay, so carboxylic acids are weak acids, and it says distinctive odors. And by distinctive odors, what that means is it has insanely bad smells. Okay, so methanoic acid is only 1 carbon. It doesn't really smell, not necessarily. However, methanoic acid is commonly called formic acid. And one of the reasons it's called formic acid is because it actually is the acid that is released by fire ants. So you get that burning from the methanoic acid. 2 carbons, or ethanoic acid, is vinegar. So vinegar has a very distinct odor. If you get really strong vinegar, it's called glacial. It really, yes, it smells like vinegar. You can get that sense of the vinegar, but it's so strong. It's almost like it assaults your nose. Like it can actually physically hurt, especially if you're sensitive to smells. So very, very, like the stuff that we use to put on vinegar is like 2%, or on our French fries is like 2%, maybe 5%. But some people are sensitive to that smell too. They don't like the smell of vinegar. Propanoic acid and butanoic acid. Propanoic acid smells really bad-ish. It does smell bad, especially if you're sensitive to smells. If butanoic acid, which is 4 carbons, if I opened a bottle of that in the classroom, it would make the entire bottom floor of St. John's smell like vomit. It smells so bad. So these acids, or sometimes are called organic acids instead of carboxylic acids. They have very, very distinct and, you could even say awful odors. So that's just something, as an aside. Really what we're going to focus on can it form hydrogen bonds with itself, and can it form hydrogen bonds with water? So there are actually 2 polar functional groups that are part of carboxylic acids. So they have an OH, and they also have a C double bond O. So the OH can form hydrogen bonds with itself or, similar molecules. And H2O. And then, of course, the C double bond O can form hydrogen bonds with only water because there's an oxygen, but there is no H. So it says it makes stronger hydrogen bonds in alcohols with similar mass. This is a really picky question. That is true, yes, because it does have the 2 functional groups, but to ask that kind of question in grade 12 is really sort of mean. But these would definitely be considered to have the highest melting and boiling point if the chain length is the same. So if you look at something called a priority list, or if you delve further into organic chemistry, there is a ranking sort of based on kind of the priority, the importance of the molecules, and carboxylic acids are often considered to be one of the top ones because they do have these 2 polar functional groups. And then, of course, always the criteria when you start to get a longer chain, so an increase in the number of carbons, then the solubility is going to decrease. And so when you have really long chains, then it starts to become less soluble in water. You can sort of think of like a fatty acid, like a lipid in your body. They do not dissolve in water, whereas smaller ones are going to dissolve better. Okay, so the ester group does have this C double bond O and an oxygen, but as you can see, it's missing the H. So this would be in between two chains. So we've used R and R prime. So we have one carbon chain. It could be however long, and this is another carbon chain. They can be the same length. They can be different lengths. It doesn't matter. Okay? And what distinguishes them is the C double bond O. So this is where maybe you want to get out some colors. So I'll use yellow. So what we're going to do is we're going to split the ester and split its name as well into, actually I'll use pink, into two chains. So the first chain the convention is that we look at the carbon chain that is attached to the single bonded oxygen. And then the second part of the name is going to be the carbon, including the carbon with the C double bond O that has that C double bond O. So the pink part we're going to write first, and the yellow part we're going to write second. So if you want, you can even color code your note here. Okay. So the first part comes from the R prime group, which is basically attached to the single O, and the yellow part, or the second part of the name, is attached with the C double bond O. Okay, so as always, count the number of carbons, and for the pink part of the name, we're going to add, so you count the carbons and add YL, like methyl is given there. And then the second part of the name, you count the number of carbons, including the C double bond O, and the ending becomes NO8. Okay? So I'm going to continue with this pink and yellow, okay, throughout my note. So if you're a color kind of person, then that might be helpful to you. So just like with carboxylic acids and really any molecule, you can count from the left or the right. That doesn't matter. It's not that we're writing the left-hand side of the molecule first or the right-hand side. What you're looking for is what part of the molecule is attached to the single O. So that would be this part here. And let me just get a better pink here. I'll pick this one, sorry. So how many carbons are in the chain attached to the single O? There are two. What is two? It's F. Oops. So then you have two carbons, so it's F, and then you add the ending YL or ethyl. And then the second part of the name is this part here, including the double bond O, don't forget that. So we've got 1, 2, 3, 4 carbons. So it's called bute because it's 4, and then the ending is NO8. Okay, so I'm going to go in and circle all the parts. So C double bond O, I've used yellow for that for all of these 3 examples here. The pink one is the single O. Okay, if you're into colors. So here now, the pink side, or the side that's single bonded to the oxygen, happens to be on the left. Again, that's not really important. That doesn't matter. You can write it left to right or right to left, similar to the way you can count and stuff like that sometimes. So try not to worry or get bogged down too much by that. Okay, so the single bonded oxygen has 1, 2, 3 carbons. 3 carbons is prop. And then you add the ending YL. Then the double bond O side, 1, 2, 3, 4, 5 is pent, and then add the ending anoate. Pink side first, 1, 2, 3, 4. 4 is butyl, and then 1, 2, 3, 4, butanoate. So this is your favorite kind of ester because both sides are the same, so you can't mess that up. Okay, pink side, we have 1, 2, YL, ethyl, and then only 1 on the other side. So that is methanoate. So most people, when they draw, because you write the methyl first, then it's easy to draw the methyl in. So again, you can still do the same thing and either use ticks, or you can use the condensed form like is typed into here. It doesn't really matter. So octanoate is 1, 2, 3, 4, 5, 6, 7, 8. And you want to make sure that when you draw it, so the ester group is on the same carbon, okay? So here I've got the O connected to this first yellow carbon. That's where the double bond O needs to go so that I've got this complete functional group. And then you go in and make sure carbon has 4 bonds. Okay. Next, we have propylpentanoate. So 1, 2, 3, single O, pent, 1, 2, 3, 4, 5, double O beside the single O. Whoops. Sorry about that. Go in with the ticks, or if you're a condensed person, you can write like CH2s and CH3s. Maybe I'll do number 4. There's lots of space there. I'll do that one as sticks if you're a stick person. Okay, decyl. Decyl is 10. That's annoying. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No big deal. We got it. And then ethanoate. Oh, nice and short. Perfect. Eth is only 2. Okay. So butyl, 1, 2, 3, 4, single O, prop, 1, 2, 3, double bond O. Okay, and then those of you that like sticks, so we go 1, 2, 3, 4, and then the oxygen, and then 1, 2, 3, and that counts. But again, if you don't like sticks, don't feel like you need to use them. Okay, that is not a requirement. All right, so esters have actually are found in nature, and they are nice odors sometimes. And so in an era where there's no COVID, what we would be able to do is you could make synthetic smells in class. So those of you that are into organic chemistry, and maybe you want to do pharmaceuticals, but you can also do food additives or perfumes. That's also a choice as well. So you would be making synthetic esters. And so one of the homework questions, I left it in there, is to draw the ester, but then also to say what the smell is. Like there's a table in the textbook with the smells, apple, banana, stuff like that. So just so you get an idea of those kind of things. So that's, again, just kind of for fun. So for solubility, they are polar. They do have oxygen. However, they do not have OH. So they would not be considered to be able to make hydrogen bonds with themselves like carboxylic acids can and alcohols. So, and tomorrow when you look at amines, which have nitrogen, so they are not, they're not going to have hydrogen bonding with themselves, which means they have lower melting and boiling points. So esters are formed by what's called an esterification reaction. So one of the things when we do the reaction lesson is we are going to look at how organic reactions often form water. Okay, so here you can see that it's a carboxylic acid because this functional group at the end, and then an alcohol has just the OH. And what's going to happen is they come together to make water. So as I said before, you do need to remember that water is HOH, okay? So it's not like, it's really not like the carboxylic acid says to the alcohol, okay, we're going to join together. I'm going to give away my OH and you're going to give away your H. However, one of the ways that you can remember how this works is to look at the difference between the functional groups. So in an acid, there is a C double bond O as well as an OH, whereas in an alcohol, there is only an OH. There is no C double bond O. So that is an important difference, okay? So keep with your colors. So before we had a carbon group attached to the single O, and I used pink. And then the carbon group that was attached to the double bond O was yellow. So you can see by those highlights, the yellow highlight and the pink highlight, and then you can see the acid has this extra OH and the alcohol has this extra H. So that's where you get the water. Actually, okay, water's blue, so I'm going to highlight blue, okay? So this OH, and this H come together to make water. And what happens in order to make sure carbon has 4 bonds? This carbon is going to connect to the oxygen, making the ester functional group. Okay, so this chain comes from the alcohol and this part comes from the acid. Why does what I've chosen to be yellow? How do I know that comes from the acid? Because an acid has a C double bond O and an alcohol does not. If you are a biologist, or if you take biochemistry, there are reverse esterification reactions, which are called hydrolysis or splitting by water. So you may have heard of that before. We're not going to really focus on that. What we're going to do is look at this esterification reaction. How can we figure out what alcohol and what acid made the ester? Okay. So it says for the following ester, so I can't print it. We're going to draw it in. Okay, and I'm actually going to add in a chlorine. Okay, actually, let's make that really obvious. I'm going to make it a bromine. Just so I think there's maybe just a few questions in the textbook like that in the homework, so just in case. Okay, so for this ester, it says draw and name the alcohol that was used to make it, and draw and name the carboxylic acid that was used to make it. So when you get this kind of the question, first of all, one of the things you can do is use your highlights. Oops. Okay, so we have the single O part goes first, right? And then the C double bond O part, I colored yellow. And why did I do that? Because I didn't really focus on this when I first did it, but now we're trying to connect it to that a single bonded oxygen is from the alcohol, and the carboxylic acid is the side with the C double bond O. Okay, that's why there's the two parts to the name. So you have a choice. This question doesn't explicitly say to name the ester. However, that is one of the things you can do to practice this. So we have 1, 2, 3, 4, 5. So pent. And then we have, this is carbon 1, this is carbon 2. We have a bromine attached to the pentyl. So you just name that like always, okay? Lowest number, say whatever it is. I erased the chlorine and put bromine only because bromine stands out more. Chlorine, it looks too much like carbon in a note, so this will stand out a little bit more. And then on the other side, we have 2 carbons, 1, 2, so that's F, and then we just have to write anoate. Okay? So it says draw and name the alcohol that was used to make this ester. So what you have to kind of think or remember, we're going to add water basically. Okay, so one of the things you can do is sort of the skeleton first. Draw the alcohol side, or the side that has the YL. Okay, but that doesn't look like an alcohol, right? An alcohol has to have OH, so that comes from the water, even though it doesn't really talk about that in this question. It's just sort of understood. Make sure you read the question carefully. This one says draw and name, okay? So 1, 2, 3, 4, 5. So 1 pentanol, and then 2 bromo. So it looks almost identical, right? 2 bromopentyl. Instead of pentyl, we've said pentanol, okay? Because it has OH. Then for the carboxylic acid, we've got 2 carbons. Okay, and then again, this isn't a carboxylic acid, right? We need this OH part from the water. So instead of ethanoate, we're going to write ethanoic acid. Okay, so you're splitting the ester into the alcohol and the acid that was making it up. Now, you might say to yourself, holy cow, but this is kind of a good question, right? First of all, you have to name the ester, then you have to draw and name an alcohol, and draw and name a carboxylic acid. So you're actually doing a whole bunch of different families in this kind of question. So when you look at the homework, there are questions like this. Take a look at them, give them a try, and then, check your answers in the solutions. And if it doesn't make sense, let me know right away, because this is a good kind of question because it tests a lot of things in only one question, right? Okay, so now this is kind of the reverse. We've got 1 butanol and propanoic acid. So this one says draw and name the ester. What I recommend that you do is, even if you just quickly sketch what 1 butanol is, okay, and propanoic acid, even if you just sketch it and you don't put in the hydrogens, then you can see sort of what's supposed to happen. It doesn't matter if you do left alcohol and right acid, it doesn't matter. So you can put the prop part first, and then remember it's going to lose its OH, and then the butanol part will be next. It's going to lose its H. The big thing is that you draw this complete, okay? So don't do something like this. Okay, that's not an ester, right? You have to have the C double bond O and the O on the same carbon. So especially here, I think, then using colors, it kind of makes it stand out more. You know, not maybe you don't have pink, but my pink part came from the alcohol and my yellow part came from the acid. So this is 1, 2, 3, 4 butyl. 1, 2, 3 propanoate. Now you may be asking yourself, well, what happens if and maybe you're not, but let's say it was 2 butanol and the alcohol was on the second carbon. What would that look like? That's beyond grade 12. Okay, so you don't have to worry about that. The questions will be where the alcohol is at the end of the chain, and carboxylic acids by definition have to be at the end of the chain. So that's what we'll focus on here. Okay, so take a look at the homework in the textbook and let me know if you have any questions. Thank you.